A further demonstration of the rationality of the irrationals. My motto? Plain honesty, simple truth, easy understanding. The joy of finding things out for yourself. Most of us with a mathematical inclination tend to be fascinated by infinite decimal expansions, particularly when, like the square roots of the integers, say root 5, we know that after multiplying by itself, we must, as logic and common sense dictate, end up with the integer we started with, since that is our definition for a square root. Comparable amongst the reals, the name given to such infinite decimal expansions, irrespective of whether they have an integer part or not, are pairs of reals that also give an integer when multiplied together, the best known example being the golden ratio and its conjugate. The golden ratio 1.61803398887 multiplied by its conjugate 0.61803398887 equals 1, so that the golden ratio and its conjugate are the reciprocal of each other. Another good example of rational behaviour by the so-called irrationals are the irrational roots of many quadratic equations. Y equals x squared plus alpha plus beta all times by x plus alpha times beta. A good example is y equals 53x minus x squared minus 34.5. We have alpha plus beta equals 53 equals 52.340859118 ... plus 0.659140881 ... Since there are those who like to perpetrate mathematical fables regarding the irrationals in order to deceive, wow, and mystify us with their brilliance, in the belief that we are just too thick to understand the irrationals, here is another example of rational behaviour from the misnamed irrational numbers. 1. Take an integer which for this demonstration is 61, since 5 cubed minus 4 cubed equals 61. 2. Take the cube root of 61, which is equal to 3.936497183 ... 3. Feed into the equation for a triangular number n squared plus n all divided by 2 to give 9.716253628 ... 4. Feed the cube root into the triangular number equation n squared minus n all divided by 2 to give 5.7797564445 ... As is to be expected, we get the same result by subtracting the cube root from the result we got in 3. 5. Square the two results we got in 3 and 4 and subtract, and the answer is 61, right where we started. The revelation is that in order to get the all-integer answer, the infinite decimal expansions must be, and indeed are, exactly the same in order to give 0 on subtraction. It's another demonstration that the irrationals are anything but irrational. The table shows the procedure applied to the difference of cubes from 5 down to 0. The irrationals with equal decimal expansion, together with their integer differences, are highlighted blue. To summarize, we have taken the cube root of an integer and fed it into the equation n squared plus n all divided by 2. We can generalize this since for the nth root we use the equation n to the power n minus 1 plus n all divided by 2. Large powers n minus 1 would require large values for n, as the roots get ridiculously small. Whilst the procedure works, the practice of using large powers is untenable and is given only for completeness. It does demonstrate that the triangular number equation is the generic one for a whole family of higher power equations. This procedure works for any integer and does not have to be the difference of 2 powers.